In this video, we are continuing our look at proton NMR spectra, and we are continuing to focus on splitting. Next, we will look at some common splitting patterns, as well as some splitting that is more complex. Let's look at a few examples of spectra. On our top left, this is the spectrum for bromoethane. And here we have our full spectrum, and then here we have the signals are zoomed in. So notice the integration is only shown on the original spectrum, and so make sure you're looking at the relative integration here and only using the zoom in for the details of the splitting. So the blue signal, if we look at this integration, this integrates to 2, so this is a CH2 group. And then the pink signal, this integrates to 3, so this is a CH3 group. But let's look at what other information we can get. So with the original signal, it's a little bit hard to tell what's going on, but if we look at the zoom in, we can see that this signal is made up of 4 peaks, and more specifically, the peaks have a relative height of 1 to 3 to 3 to 1. Also notice that the spacing in between these two peaks is the same as between these two peaks, is the same as between these two peaks. So here our intensity is 1 to 3 to 3 to 1. This is a quartet. A quartet, we've got our 4 peaks, so that means that the hydrogens that give rise to the signal have 3 neighbors. So keep in mind, when we're looking at the compound and we see how many neighbors there are, we know that the number of peaks will be n plus 1. Now we're going in the other direction. Because we have 4 peaks in this signal, we have to take 4 minus 1 to tell us how many neighbors we have. So by integration, we know that the blue signal is a CH2 group, and by splitting, we know that the CH2 group is next to a CH3. So the blue signal tells us we have a CH2 and it is next to a CH3. Actually, this tells us we have 3 neighbors. It's possible to have a CH2 on one side and a CH on the other side, but the simplest possibility is that it is a CH3. Next, if we look at the pink signal, here we are zoomed in, and we can see that we have 3 peaks, and these have an intensity of 1 to 2 to 1. So a 1 to 2 to 1, this is a triplet. 3 peaks minus 1, so there are 2 neighbors. So based on integration, we know that the pink signal is a CH3, and based on the splitting, we know that it could be next to a CH2 group. If we also take into consideration the chemical shift, this is a little bit higher than normal. This is definitely a lot higher. It must be next to something electron withdrawing, such as a bromine. So what we have here, CH3, CH2, Br. If we call this signal A, then this would be signal A. If we call this signal B, then this corresponds to B. An ethyl group is a very common feature in structures, and so the ethyl splitting is going to be a common occurrence in NMR spectra. So if we have a signal that integrates to 2 hydrogens and is split by 3 neighbors, and another signal that integrates to 3 hydrogens and is split by 2 neighbors, then this is what we see for an ethyl group. Next, we have another proton NMR spectrum. Here is our original spectra, and then here we have the zoom in of the peaks. The relative integration, if this is 1, then this is 6. So we have our blue signal is a CH group, and then our pink signal, it's actually H6, so we must have 2 CH3 groups. If we look at the zoom in of the pink signal, we can see that it is a doublet. We have 2 peaks of about equal height, and so this is a doublet, which means the hydrogens that give rise to this signal have only 1 neighbor. Looking at the blue signal, we have 1, 2, 3, 4, 5, 6, 7. So this is a septet. which means there are 6 neighbors. Notice how well this fits. This integrates to 1 and has 6 neighbors, whereas this integrates to 6 and only has 1 neighbor. So this is what we commonly see for an isopropyl group. And this is the spectrum for this compound. So A and B. A is this hydrogen. It is deshielded because it is next to the chlorine. It integrates to 1 because it's only 1 hydrogen. And it is split into a septet because it has 6 neighbors. Then these would give rise to signal B. It integrates to 6 because we have 6 hydrogens. It is split into a doublet because there is only 1 neighbor. And it shows up close to 1 because it's a little bit further removed from anything electron withdrawing. A septet that integrates to 1 hydrogen and a doublet that integrates to 6 hydrogens. This is a common feature when we have an isopropyl group. There are a couple of other things that I want to point out. One of them is about this septet. Because this is only 1 hydrogen, on the overall spectrum, the signal from the 2 CH3 groups is going to be much taller. This signal is going to be much shorter. Even when we zoom in, keep in mind Pascal's triangle, the difference between the first or the last and the center, it's a really, really big difference. So these little itty bitty peaks, sometimes it's hard to see them and they might get lost in the background noise. So maybe you can only see these 5 peaks and you're not quite sure about 6 and 7. Sometimes you might want to say that, well, I know this group of hydrogens is next to a bunch of hydrogens, but I'm not exactly sure how many it is. You could try to look at the relative intensities to figure out what it might be, but sometimes you'll just have to look at it and say, this group has lots of neighbors. And then other information will allow you to fill in those gaps. Another feature that is important is about the size of the splitting. So the spacing between these 2 peaks is the same as this spacing is the same as this spacing, but it's also the same as this, which is the same as this. Now that spacing is not the same for every single set of hydrogens, but it is the same spacing within a regular pattern, a triplet, a quartet, a pentet, and that gap is the exact same between the 2 signals that split each other. So when we think about splitting, when we think about the size of that little gap here or here or here, that is the J value, also called the coupling constant. The J value is given in Hertz. Now, when you have a set of hydrogens and another set of hydrogens splitting, first of all, they will both split each other. The splitting is reciprocal, and they will have matching J values or matching coupling constants. Often by looking at the coupling constants, that can help you to identify which set of hydrogens is a neighbor to which other set of hydrogens. Obviously here we only have 2 sets of hydrogens, and so they split each other. But if we are looking at a more complex molecule, we would have a more complex spectrum. Between these peaks and these peaks, the J value will also be the same. However, this hydrogen splits these will split this one by the same amount. Next, let's talk about some more complicated spectra due to more complicated splitting patterns. Earlier, we talked about looking at an HA, and on the neighboring carbon, there were 2 HBs. What if our hydrogen has 2 neighbors, but the 2 neighbors are different from each other? So HA has the neighbor HB, and it has the neighbor HC. Now, HB is not equivalent to HC, but the size of splitting, so how these 2 affect each other compared to how these 2 affect each other, there are 2 possibilities. If the J value for the AB coupling, so that would be this J value, is the exact same as the coupling constant for the AC splitting, so this splitting. We can represent this with an upside down tree, and we think about this is the hypothetical ppm value for HA only based on electronic effects. But HA can be split by HB, and so this is the JAB. So the coupling constant between A and B. So this is where A absorbs just based on the electronic environment. And then if HB is pointing up or pointing down, then this gets split into two. So instead of seeing this, we would see 2 due to the neighbor B. But A is also split by C. So this is going to be split into 2, and this is going to be split into 2. So this is the J for the AC. Now, if the coupling constant for AB is the exact same as the coupling constant for AC, then when these split, these line up on each other. And what we end up with is a 1 to 2 to 1 triplet. So even if the hydrogens are not chemically equivalent to each other, it's possible that the coupling constants are the same. And in that case, having two different neighbors kind of acts the same as if you had two neighbors on the same carbon. If we have alkyl groups, then a hydrogen and its neighbor will typically split each other by around 6 to 8 hertz. So it's quite possible that the JAB would match the JAC. But if we have different types of hydrogens, let's look down here some more. I just referred to it, but this is a table from the McMurray textbook, and here are some approximate values of the proton coupling constants, all given in hertz. So our adjacent hydrogens in regular alkyl groups, the J values tend to be around 6 to 8 hertz. On an alkene, the two hydrogens connected to the same carbon have a very small J value. Now notice if we have our hydrogens trans to each other or our hydrogens cis to each other, we get a different range. So by determining the J value, we can figure out whether our hydrogens are cis to each other or trans to each other, right? So we have different possibilities for common J values or coupling constants, and some of them are quite similar, but some of them are significantly different. So let's come back to this molecule up here. Now, still HB is not chemically equivalent to HC, but what if the coupling constant for AB is not the same as the coupling constant for AC? Well, let's say this is the coupling constant for AB. So this is a really big coupling constant. Maybe this is a vinylic trans hydrogen, for example. So instead of HA absorbing here, it will be split into a doublet by hydrogen B. But where it would absorb due to hydrogen B, this is also split by C. So this is the J value for the splitting between A and C. So the J value between A and B is bigger than the J value between A and C. So that when this is split into two, the splitting does not come back over here and meet, right? They don't line up again here. Instead, we have a 1 to 1 to 1 to 1 intensity. Notice also, if we're just looking here, this gap is the same as this gap, but this one is different, right? If we have our triplet, for example, this gap is the exact same as this gap. If we have a quartet, then this distance is the same as this distance is the same as this distance. So this does not give us a quartet. First of all, because it's 1 to 1 to 1 to 1, not 1 to 3 to 3 to 1. But it's also not a quartet because the spacing in between are not the same. This spacing will be the same as this spacing, but this is different. Now, this splitting pattern is called a doublet of doublets, which is symbolized DD. It's also possible to have a doublet of triplets, a triplet of doublets, a triplet of triplets, and it can get, you can have a doublet of doublets. So it all gets very interesting. And there are more complex patterns that we could see, and there are ways that they can be interpreted. In general, for the spectra that we'll be looking at in lecture, I want you to be able to recognize a singlet, doublet, triplet, quartet, and so on, but not necessarily the doublet of doublets or triplet of triplets. When we are in lab, we will be looking at some more complicated spectra, and in some cases, you will need to use some of these different J values to get information. So although we're not going to look at very complicated things in lecture, I want you to be aware of it, especially so that you could dig in a little bit deeper in lab.